In this lab, we will explore Newton's second law, which is net force equals mass times acceleration. To do this, we will examine an object moving at a constant velocity, meaning there is no acceleration. In this model, the object is a large ball being rolled across a tile floor. In this system, we assume the net force acting on the object is zero. The axis is set so the ball is moving in the positive x direction. The mass of the ball is 1 kilogram and the diameter is 65 centimeters. If the x and y axes were inversed, the x values and y values would be switched. The velocity vector would change in direction but not magnitude. We will now view the ball moving across the floor at a relatively constant velocity and then compare this to our computational model. The relatively linear graph shows that the ball was moving at a relatively constant velocity. Now let's look at the code used to write our computational model. The mass of the ball is 1 kilogram, and the initial position from tracker is 0.005 meters. To get the initial velocity, we use the first two data points in tracker to find the change in position over the change in time. The ending time obtained from tracker was 1.75 seconds, so that is when we choose to end the system. The net force assumed for this computational model is 0. The velocity equation relates directly to Newton's second law. However, because the net force is assumed to be 0, there is not supposed to be a change in velocity, and V final is supposed to equal the initial. The ball position is then determined by the original ball position plus the average velocity times delta t. T is then equal to the original time plus delta t. And here is our computational model representing the ball's movement. As you can see, this model is completely linear, which means the object is moving at a constant velocity the whole time. And this differs slightly from our observed model. We will now compare our computational model with our real-world observations to see how well our model predicted the ball's movement. Here you can see how our computational model and observed movement of the ball compare. As you can see, the blue line representing the ball's actual motion did not follow the predicted motion. This is because there were external forces acting on the ball, and these were not accounted for in the computational model. Forces that could have affected the ball's movement are gravity, friction, and the slope at which the ball moved.